Today, we're going to continue our discussion of normal probability distributions by talking about sampling distributions and estimators. So, a sampling distribution of a statistic, we're going to talk about what that is, and we're going to talk about how we can find values of statistics that we obtain from a population. So, general behaviors, all right? So when we have samples of the same size that are taken from the same population, we have two properties that are going to apply. The first is sample proportions tend to be normally distributed, and the second is that the mean of sample proportions is the same as the population mean. So what we mean by that, here we have proportions. We're going to randomly select n values and find the proportion for each sample. And so we'll have this collection of sample proportions that we gather. When we look at the probability distribution of those, it's going to look normal. Similarly, if we look at sample means, the same thing happens. So we randomly select n values, and we're going to find the mean for each of those samples. And so we'll end up with this collection of sample means that we'll be working with. We look at the probability distribution of those sample means, and again, normally distributed. And finally, another one we might want to look at is variances. So again, randomly selecting n values, finding the variances for each. We have the collection of sample variances. We look at the probability distribution. And what we generally see here is a skewed to the right distribution. So let's look at the definition of a sampling distribution of a statistic. This is a distribution of all values of the statistic when all possible samples of the same size, n, are taken from the same population. So we usually represent this using a probability distribution in the format of a probability histogram, a formula, a table, something like that. So that's the general definition. Let's take a look specifically with sample proportions. So the sampling distribution of the sample proportion is the distribution of sample proportions, or the distribution of the variable p hat, with all samples having the same size n taken from the same population. And again, we generally display them, represent them the same ways. So some notation for proportions. So distinguishing between a population proportion and a sample proportion, we'll use p as the population proportion. We'll use p hat as the sample proportion. Right. So behavior of sample proportions. So the distribution of sample proportions tends to approximate a normal distribution, and sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions is equal to the population proportion. Okay, so if we say something targets a value, it means that the mean of all the sample proportions, means whatever, they are equal to the population proportion, mean whatever, all right? Also, that means the expected value of the sample proportion, or mean, is equal to the population proportion, or mean. So let's take a look at an example. So let's say we were going to roll a die 5 times and find the proportion of odd numbers. So we want to think about, what do we know about the behavior of all sample proportions that are generated in this process if it continues indefinitely? So here we have a figure, and we can see that if we're looking at how many of the 5 times, or of the 5 die are odd numbers, we can have 1, 2, 3, 4, or 5 of them. So we'll have 0.2, 0.4, 0.8, and 1 and 0 as our possible sample proportions. And when we take a look at what all of those sample proportions, if we did this forever and ever, so this figure is if we did it 10,000 times, but to get the true version, we would have to do this indefinitely. But the histogram, the probability histogram, has values between 0 and 1, and we look at what this falls at, and we can see that the mean falls at 0.5, and it looks approximately normal. So our population proportion is 0.5, which is approximated here. All right, and that's exactly what we've got here. So now let's talk about with the sample mean. It's the same thing, except for we replace the word proportion with the sample mean. Okay, so again, sample means tend to be normally distributed, and the sample means target the population mean. So again, let's think about rolling a die 5 times to randomly select 5 values from the population, and then we're going to find the mean of the results. So let's take a look at what we know about the behavior and what happens if this continues indefinitely. So here again, we've done this 10,000 times. We would have to do it indefinitely to get the true value. But taking the mean of all of the numbers that we roll, they can range from 1 to 6. And so we've got this probability distribution given as a histogram with all the values that can happen between 1 and 6 for this mean. And we see that's approximately normally distributed, and the mean, the population mean, is approximately is the mean of our distribution we have here. So our mean is 3.5. And again, that's what this is telling us. So now let's take a look at the variance. So the sampling distribution of the sample variance is again the distribution of sample variances with all samples having the same sample size taken from the same population. Same deal, all right? So remember our population standard deviation, we know how to calculate that, and also the variance. So some behavior of sample variances. The distribution of sample variances tends to be a distribution that's skewed to the right. But even though that's the case, the sample variances target the value of the population variance. So that is the mean of the sample variances is the population variance, even though it's not normally distributed. So again, let's roll that die 5 times and find the variance of the results. So we're going to find some sample variances and think about what we know. So we're going to repeat it 10,000 times. Again, we'd have to do it indefinitely to get the real deal. But with our 10,000 times, we can already see it's skewed to the right a little bit with that distribution. And we have values, again, ranging from 0 on up of possibilities of variances here. And so we see that skewed right behavior. But again, the mean of these variances is 2.9, which is going to be our population variance. Right? And again, that's what we have here. All right, so now let's talk about estimators. So an estimator is a statistic used to infer or estimate the value of a population parameter. When we talk about having unbiased estimators, what we're talking about is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. Okay, so some examples of unbiased estimators are the proportion, the mean, and the variance. And some examples of things that you've seen that are biased estimators, they don't fit that deal with the statistics targeting the corresponding population parameter, are the median, the range, and the standard deviation. So really quick, when we're talking about all of this stuff, we've been talking about dealing with sampling with replacement. So there's two important reasons for that. The first is that it doesn't matter whether we're replacing or not when we're selecting a relatively small sample from a large population. There's no significant difference whether we're replacing or not, so we can just assume that we are. And the second reason, if we're taking a larger sample from a smaller population, so the difference isn't so big, it's important that we are replacing. We want to be able to do that so that we have independent events. So the events are not affected by previous outcomes. And the reason for that is because it's so much easier to analyze data and get us calculate or do our calculations and deal with formulas when we're dealing with independent events rather than dependent events.